Good afternoon everyone, especially to our Professor Engineer Dan Vincent L. Intuna. Good afternoon, sir. So our topic to discuss today is long and slender columns. A long or slender columns is the one of the ratio effective length to its length is not less than 12. When this ratio of effective length to the less radius of gyration is greater than 45, then it is called a long column. It is subjected to a bending moment and in addition to direct compressive stress. The load carrying capacity of a long column is than a short column. P delta moment. So, unsa day role sa P delta moment? Mulaktaw sa tada guys. So, kung inyong tanawon ang drawing, na siya ay nakaaraw na mao na ang kolom, ang rectangle nga pataas. So, subjected man siya sa axial force. Tanawon ninyo ang north ug ang south. Sa north, namoy makita nga araw nga nabawag na curve. Mao na ang iyang positive bending. While ang sa south na nabawag hapon, mao na siya ang south bending. So ang tendency kung naay positive bending o negative bending, na siya'y tendency nga magka-deflection, which is nga ato nang gitawag og delta. So ang moment nana siya'y duha ka klase, ang primary moment o secondary moment. Pero usa ta mo kuan nga na og unsa na sila, mobalik sa ta diri atong basahon ang P delta moment. P delta moment mao ni siya when a column is subjected to primary moment M such as those caused by applied load or joint rotation. The axis of the member deflects laterally. This deflection causes additional moment applied to the column which is equal to the column load times the lateral deflection. This moment is called secondary moment or the P delta moment. So inyong tanawon nabajay na deflect sa kilid, di ba? There is illustration. If the secondary moment becomes too large, so kung ang atong secondary moment dako ra kaayo, the column is said to belong or slender column. Mao jud ay atong hinumduman kung ang atong secondary moment dako na kaadyo. So dako ang atong column, long or slender column. And it is necessary to design its section for the sum of the both primary and secondary moments. However, the code permits the columns be designed as short column if the secondary or P delta does not reduce their strength by more than 5%. So, agsahong giingon ninyo na atoy duha ka type sa moment, which is ang primary moment o secondary moment. Unsa daining primary moment? Mao ni siya ang maximum end moment sa inyong makita dire. While ang secondary moment, mao ni siya ang effect of P delta moment. Kuwangan dinig F ning atong effect, wrong ang mga spelling nga ni. Pagpasensya So para makuha nato ang P delta, ang effect sa P delta moment, ato na siyang ang axial load at P ato na siyang multiply dito sa deflection. So naa may mga factors ang pagkuha sa slenderness, sa ang effect sa slenderness. Mao na siya ang mga factors. So ang una, unsupported length of compression members should be taken as the clear distance between floor slabs, beams, or the other members capable of providing lateral support for the compression member. Where columns capitals are present, unsupported length should be measured to the lower extremity of capital in the place considered. So ang inyong hinumduman nga ng unsupported length of compression members, na ni siya ay clear distance dapat kanunay. While ang effective length factors for the compression members brace against sidesway, effective length factor K should be taken as 1.01 unless analysis shows that a lower value is justified. So ato ra ning i-tackle, ato ning i-discuss more inig sa sunod pa nga mga slides. Ato sang laktawan. For compression members not braced against sidesway, effective length factors K should be determined with the due consideration of effects of cracking and reinforcement on relative stiffness. So ang kaning relative stiffness guys, gitawag ni nato og EI or mas gitawag nato og flexural rigidity and should be greater than 1. If there were such a thing as perfectly pinned in column, its effective length would be its unsupported length. The effective length factor K is the number that must be multiplied by the columns unsupported length to obtain its effective length. So kakita mo sa illustration guys, mao ni ang ilang mga equivalent sa ilang K, which is ang effective length. Ito sang laktawan. So sa first nga illustration makakita mo og pen kung ang imong column is both is pinned at both sides, ang value sa atong K takes as 1. Makita man mo guys no nga puro P ng number ang kanang kinaunhan nga illustration ang E. So ang B laktawan sa nato na. Then kung fixed end gani, there are 2 point of inflection. Kung inyo makita na siya ay duha ka arrow na siya duha ka tuldok point. So para ma-solve na to ang effective length, ato na siyang i-solve from the distance sa duha ka point of inflection. Diha jud ta kanunay magtan-aw guys kay kung fixed end gani na siya itulo ka and then kung pinned gani og unfixed end, if the one is fixed and the other one is pinned, ang atong effective length nato is 0.7 sa D na nato guys. So sa fixed end di ay nakalimot ko ang ato dayong K nga na 0.5, nakalimot ko mention. So effective length factors for unbraced columns. The base of this particular columns is assumed to be fixed, whereas its upper end is assumed to be completely free to both rotate and translate. The elastic curve of such a column will take the shape of the elastic curve of a pinned in column of twice its length. Its effective length therefore equal to effective length as shown in the figure. Kani siya guys, kaning B. Mao ni siya. Kung fixed gani na siya og ang iyang tumoy pre-ends na siya, so automatic jud na siya ang iyang K2. So ang modiska sa type of column si Binhor Malunas. Salamat.
So this is the continuation for the plus zero. Radius of gyration R. The radius of gyration introduces the effect of cross-sectional size and shape to slenderness for the same cross-sectional area. A section with higher moment of inertia produces a more stable column with a lower slenderness ratio. The radius of gyration R is defined below. So the formula of radius gyration is R is equals to the square root of moment of inertia over the area. It is permissible to use the approximate of R is equals to 0.38 H for square and rectangular section, and R is equals to 0.25 for circular section, where H is the overall sectional dimension and the direction stability being considered. So the circular section using the R equals 0.25 is a circle. The sectional of radius of gyration using 0.3 is the square and rectangular. So lateral bracing and designation of frames as non-sway. Frame is considered to be non-sway if it is sufficiently braced by lateral bracing elements. The structural walls, otherwise it may be designated as sway frame. Frames that provide resistance only by columns are considered to be sway frames. Structural walls that appear in of elevator shafts, stairwells, partial building enclosure, or simply used as interior stiffening can provide substantial drift control and lateral bracing. In most cases, even a few structural walls sufficient to brace a multi-story, multi-bay building. The designer can usually determine which frame is non-sway or sway by inspecting the floor plan. Frames with lateral bracing elements. The total lateral stiffness of the bracing elements provide at least 6 times the summation stiffness of all the columns may be classified as non-sway. So here's the example of non-sway frames and sway frames. Here's another example. The sway frames here has an unbalanced horizontal force, so it sway. If it's have another in the opposite side, another have horizontal force, it will become a non-sway frame because it's balanced. Here in the non-sway frames, you see that there's a vertical load in the midspan, so it won't. So it's considered non-sway. It won't sway because it is in the middle. If it is in here or in here, it will be unbalanced. It will be go down. So the difference is in the non-sway frame is an unbalanced horizontal force. So design of cylinder column. Design of cylinder column should be based on second order analysis which incorporates member curvature and lateral drift effect as well as material non-lateral and sustained load effects. An alternative approach is specified in for columns with slenderness ratios not exceeding 100. This approach is commonly referred to as moment magnification method and based on magnifying the end moment to account for secondary stresses. The application of this procedure is outlined in the following section. So this is the slenderness column in non-sway frames. The slenderness effect may be neglected for columns in non-sway frame is followed inequitably is satisfied. So the formula of non-sway frames. So m sub 1 over m sub 2 is the ratio of smaller to larger end moments. This ratio is negative value when the column is bent in double curvature and positive when it is bent in single curvature. All stress column and figure double curvature columns in non-sway frames are stable when they bend double curvature. Slender columns non-sway frames are designed for factored axial force V and amplified moment MC. The amplified moment is obtained by magnifying the larger of the two ends moment M2 to account for. So member curvature and resulting secondary moment between the supports while the supports are braced against sideways. If MC computed for curvature effect between the ends is smaller than the large end moment M2, the design is carried out for M2. So the formula. So this is the single curvature and the double curvature. Single curvature positive, the double curvature negative. So the formula for the due to consideration given the section as specified approximately using this formula. So cylinder column and sway frames. Column and sway frames are designed for factored axial load Pu and the combination of factored gravity load moment and magnified sway moments. This is specified below an illustration picture. So the formula, musindra ko sa picture o di maklaro, mong maglahi ko picture sa kanya para maklaro. So this is the design moment, its wave frames, the gravitational load moment, the magnifying load moment, and the sway moment. So na-notice ninyo na nasi jay horizontal, unbalanced horizontal force mao nang ning sway siya. In sway frames, all the columns of a given story participate in the sway mechanism and play roles in the stability of individual column. Therefore, which give the summation of factor axial and loads and critical loads for all the columns in story. Respectively, the critical column load P can be computed with the effective length factor K computed for unbraced columns and B ratio maximum factor sustained share within the store for the maximum total share provide an average for all columns in store. Therefore, it is an acceptable result if all the columns in the store undergo the same storage drift when significant torsion is anticipated under lateral loading. A second order analysis is recommended for finding the amplified. So, mag-send ako sa kanang klaro na katong sa mga formulas. Thank you, sir. That's all.
So hello, we have the sample problem for design of slender columns, in which the problem is determine the column in the brace frame shown in figure is short or slender. The concrete strength is 25 Newton millimeter squared and the ultimate axial load is 1280 kilonewton. So this it has effective length of 3 meters. Beam on the we have the same length of this beam, and the length of each other side is 6 meters and 4 meters, and the column beam size is 300 times 700. This incoming beam is 300 times 500 with the length of each other side of the column is 4 meters. We have the cross section here of the column 300 times 400. So we have to go a series of calculation to determine the effective height of a column and to the slenderness ratio and to figure if it is short or slender. So we have here the higher slenderness ratio at y-axis, the smaller depth, which is 300 millimeters, less stiff beam size is 300 millimeters times 500 meters. First, we need to find the effective length of a column. So it is here. The equations of effective length is given here, and this means for the brace frame within there is K1 and K2. K1 and K2 represent the relative flexibilities of N1 and N2. To determine K1 and K2, we need to find the second moment of inertia, which is here, and overall weight of the beam, so which is 400 times 300 squared over 12, which the overall weight of the column is 900 times 10 to the power of 6 millimeters. The moment of inertia and overall weight of the beam, which is 300 times 500 squared over 12, is equal to 3125 times 10 to the power of 6 millimeter, which is the overall weight of the beam. Then use for the equations K1 and K2. So substitute this relevant value into equations 2. Here 3000 here is the effective of height. Then effective length rather. Then the 4,000 here is the length of incoming beam, and we found out this equation is 0.096. Then substitute the value into this equation. So we have here 0.51. The square root of 1 plus 0.96 over 0.5 plus 0.096, which is same as here. We found out that it is 0.59 times to the effective length, which is 3, is equal to 1.764 meters. So we have this radius of gyration. With the equation here, we have to substitute the value, which is square root of 900 times 10 to the power of 6 over 300 times 400, which is 86.6 meters. And the slenderness ratio here 1764 over 86.6, which is 20.4. So we found for a brace column, the minimum limiting value of which is this to 26.2 over the square root of 1280 times 1000 over 300 times 400 times 25 over 1.5 is 32.7. So in here the slenderness ratio is less than to the brace cut of this brace for the brace column. So we found out the slender check that 20.4 is less than 32.7. So in the slender check, it is short column.